This lecture covers a very important survival regression model, the Cox regression model. And Cox regression model is what's usually viewed as a kind of semi-parametric model. It is parametric only to a certain extent, and it is non-parametric for part of the model, and later on I'm going to get into details about it. The Cox pH regression model, or the Cox pH regression model, takes the form of a lowercase h of t given covariates. So here, h is the hazard function again, and then this hazard function can be decomposed into two components. First is the baseline h0. Then multiply by exponential function of xj and beta x, so covariates. And the h0 baseline hazard is given no particular parameterization and left unestimated. So that's the reason why it's called semi-parametric, because this part is non-parametric, okay? And no assumption made about the shape of hazard over time, okay? So that's the non-parametric part of the Cox regression, or Cox proportional hazard regression model, okay? The Cox proportional hazard regression model has no intercept, okay? Let's say, pretend that we add an intercept to the model, okay? Here, right? We add an intercept here. We say, well, we don't know this baseline hazard, but what about adding this intercept to the model? Well, what happens is that after we combine, the baseline hazard and the exponential function of beta 0, it turns out, these two terms can be absorbed into a single component, and they're undistinguishable from each other, right? So here we have beta 0, right, plus xj beta x, and then we can take out, this part and combine it with baseline hazard, like here. So the baseline h0t, that's the original baseline hazard, multiplied by the exponential function of the intercept beta 0 is our new baseline hazard. The value of beta 0 is undefined because any value works as well as any other. Or, in other words, these two parts are not distinguishable or identifiable from one another, okay? So that's the reason why in a Cox pH regression model, we don't have intercepts, okay? Next question is how to estimate the model. Note that in Cox regression model, the baseline H0 T, that is the baseline hazard, is unspecified, and will cancel from our calculations while the binary outcome analysis at the individual failure times. The technical details is not provided here. But in general, the likelihood function, okay, of Cox regression can be decomposed into separate individual likelihoods, okay? That is, the likelihood of the event to be observed occurring for subject I at time ti can be written as follows, okay? As follows. So this is the individual likelihood. okay, for subject I at time ti. Okay, so we construct exponential function of this subject. Okay, covariates z, and its associated, parameter coefficients beta in the numerator. And what's in the denominator is the sum of all the exponential function of all the subjects in the risk set. So RTI is the risk set. That is all the individuals that are at risk of failure at time ti. Okay, so once we construct this individual likelihood, and what we're going to do is we can multiply through all this individual likelihood for distinct individuals across distinct time points. Okay. Then here we have a little bit of complication because sometimes we could have multiple cases that fail at the same time. So what is called tied survival times. In that circumstance, adjustments, including Afron, Breslow adjustments have to be made for such tied survival times. And here, we won't get into technical details because they're beyond scope of this class. So in summary, we perform one analysis per failure time, per subject in this case, without getting to tied survival times. And each analysis returns the probability or likelihood of failing for those who did in fact fail at that time. So here we're talking about this individual likelihood. And what we're going to do, we multiply through. Okay, and this likelihood, okay, this final likelihood is a product of this individual likelihoods. And these individual likelihoods are what Sir Cox, the statistician who invented this model, what he calls the partial likelihood or conditional likelihood. Okay. So once the likelihood function is established, what we're going to do, we simply use maximal likelihood estimation to estimate this parameters, okay, the beta, right, and get the results. Again, here I'm not going to get into details since I already covered the kind of technical details in previous sessions on maximal likelihood estimation. Next is interpretation. Very similar to the interpretation of results from proportional hazard exponential regression models. Okay, very similar. So here we have this hazard function, right? And we don't know the baseline hazard. It doesn't matter because we don't have to explain or provide interpretation for the intercept, right? Usually intercepts are not the quantity of our interest. What we're interested in are those slopes for covariates, right? So here again, let's say we have this generic variable x2. And what I'm going to do is I want to increase x2 by 1 unit. So the initial hazard function going to change to this new hazard function, right? Still this unknown baseline hazard. And also within the exponential function, we have x2 increased by 1 unit, right? Then what we're going to do next, you would expect, we're going to take a ratio of the initial hazard function, right, in the denominator, and this new hazard function, what we get? Okay, we get the exponential function of the coefficient corresponding to the generic covariate x2. And what's going to be an interpretation? Well, if you remember, basically what we're going to say is holding all other variables constant for each unit increase in x2, we would expect the hazard rate to change by a factor of exponential raised to power, exponential function of beta 2, okay, depending upon whether the exponential of beta 2, exponential function of beta 2 is greater than 1, then we say, well, we would expect the hazard rate to increase. Well, if the exponential function of beta 2 is bound between 0 and 1, then we're going to say, holding all other variables constant for each unit increasing x2, we would expect the hazard rate to decrease by a factor of the exponential function beta 2, given that the beta 2, exponential function beta 2 is bound between 0 and 1. Okay, so this is just, for a generic variable x2, and the same interpretation is applicable to all other covariates. Right here, I'm just using a very generic variable here.